Interstellar targets, there's no second chance. Still, into the silence, rumors spread. Some speculated that classified satellites had captured images too sensitive to release. Others suspected deliberate story management to prevent panic over a potential anomaly. A few believed the data were simply so strange that scientists were struggling to make sense of them. The modern media landscape only fueled the speculation. Bright, photogenic comets trend easily. 3 Atlas, with its scattered updates and blackouts, slipped from attention. After Gemini's early September images, online engagement briefly spiked, only to drift toward conspiracy hashtags as the blackouts stretched on. Behind the scenes, though, the reality remains steady. Every dataset grinding through a meticulous multi-stage pipeline designed to catch errors and prevent premature claims. Compared to the open flood of data during Oumuamua's discovery, or Borisov's steady cadence, 3I Atlas felt painfully slow. But the difference was not secrecy. It was a collision of technical constraints, proprietary policies, and multi-agency review. The next clear opportunity to observe 3I Atlas came not from Earth, but from Mars. On October 3rd, the comet swept past the red planet at a distance of just 19 Australian dollars, around 28 million kilometers. In cosmic terms, this was a remarkably close approach, though still far beyond the reach of detailed imaging. The event offered a rare chance for Mars-based spacecraft to step in. While Earth's flagship observatories remained locked out by solar geometry, the ExoMars Trace Gas Orbiter, equipped with the Cassie camera, and NASA's Mars Reconnaissance Orbiter, with its powerful HiRISE instrument, attempted to capture the flyby. Both instruments are legendary for their sharpness when it comes to Martian terrain. Cassie is celebrated for 5 per pixel detail of the surface, while HiRISE can resolve features down to about 34 centimeters per pixel in orbit around Mars. But at tens of millions of kelvin, those capabilities diminish dramatically. Each pixel suddenly stretched to cover hundreds of kilometers of space. The comet's nucleus, somewhere between 320 and 5.66 kilometers across, would appear as nothing more than a single unresolved, too small for even the best optics to tease apart. This limitation meant that anyone hoping for crisp close-up images of 3 Atlas from Mars was bound for disappointment. The instruments were never designed to track fast-moving deep space objects. Their exposure times had to be short to avoid smearing, and the signal-to-noise ratio dropped quickly as the faint comet streaked across the background stars. In essence, the Mars orbiters could not reveal structure in the coma or the tail. They could not show jets, plumes, or the shape of the nucleus. What they could provide, however, was still valuable photometry. By measuring 3 Atlas's overall brightness from Mars orbit, scientists could gain an independent check on the comet's activity. Such data are particularly critical when Earth-based telescopes, and especially the big flagships, are sidelined. A sudden brightening during the flyby might point to an outburst or fragmentation event. A steady light curve would suggest a more stable release of volatiles. Just as important, the Mars spacecraft could relay their observations quickly. Both the Trace Gas Orbiter and Mars Express have streamlined data pipelines capable of downlinking and processing within 24 to 48 hours. In a period of silence from Earth's primary instruments, even a simple dot of light, if measured precisely, could break the information drought. With the Mars encounter behind it, 3 Atlas moved toward another critical moment, perihelion. On October 29th or 30, the comet would pass closest to the Sun at a distance of about 1.36 astronomical units. This was not close enough to make 3 Atlas a true sun grazer, but the encounter still promised to push the nucleus to its limits. Rapid heating, high velocity, and the stresses of solar radiation could destabilize the surface. Would 3I Atlas's nucleus hold together, or would it fracture under the strain? For observers, perihelion offered several key signatures to watch. The most obvious was the light curve. A smooth rise in brightness followed by a gradual decline would suggest a relatively steady release of gas and dust. Sharp, irregular spikes, on the other hand, could indicate surface outbursts or even fragmentation. A single jump in brightness would not be enough to claim a breakup. Patterns confirmed by multiple observers would be essential. Another expected marker was the behavior of the comet's antitail. This is the curious sunward-pointing spike of dust that can appear in wide-field images created by particles aligned with Earth's orbital plane. As Earth's perspective shifts, the antitail can flip, fade, or intensify. For 3 Atlas, models suggested the antitail would reach its most dramatic appearance near perihelion, only to diminish rapidly afterward as the geometry changed through November into December. Tracking its orientation across successive images would offer important confirmation of dust dynamics and orbital details. Color was also on the watch list. Amateurs had already reported a greenish hue in 3I Atlas's coma, likely due to molecules such as dicarbon or a cyanogen fluorescing in sunlight. But if that green glow faded or shifted after perihelion, it might signal the depletion of certain ices or the exposure of fresh material from within the nucleus. Without spectra, though, images alone would not be able to prove what was changing. Only renewed access to Webb and Hubble could settle the question. That access was expected to return in December. As 3I Atlas's elongation from the Sun widened, both flagship telescopes would be able to target it once more. The community anticipated a wave of new observations. High-resolution imaging from Hubble, spectroscopy from Webb, and a chance at last to verify whether carbon dioxide truly dominated its composition. These data could also resolve whether the brightness scatter reported earlier reflected real changes in the coma or simply inconsistencies in measurement. Looking still further ahead, orbital dynamics suggested another intriguing possibility. If 3 Atlas survived its solar passage intact, a favorable geometry near Jupiter in 2026 might provide another opportunity for study. The comet's journey was far from over, and its long arc through the solar system promised future windows for discovery. For now, though, the picture remained incomplete. What astronomers knew about 3 Atlas was striking. A coma hundreds of thousands of kilometers wide, a plume shifting unpredictably, hints of unusual chemistry, brightness measurements that refused to align, and a green tint that seemed brighter than in most comets. What they lacked was certainty. No peer-reviewed spectra had yet confirmed the suspected carbon dioxide dominance. No definitive explanation had accounted for the scatter and brightness data, and no consensus had been reached about the comet's shifting color. In the meantime, frustration and speculation filled the gap. Amateur astronomers posted nightly images comparing notes across continents. Professionals urged patience, explaining that the blackout was not a choice but a consequence of orbital mechanics and careful procedure. Yet the waiting felt like absence, and absence felt like secrecy. Between the hard limits of telescope design and the deliberate caution of the scientific process, the story of 3 Atlas became one of fragments and anticipation. It was a reminder that in astronomy, even in the age of instant information, some discoveries still unfold at their own pace. The case of 3 Atlas illustrates the tension between how science is practiced and how it is perceived. Scientists prioritize caution, careful analysis, and accuracy. The public, along with many amateur astronomers, crave immediacy and openness. Silence, even if built into the system, feels like secrecy. In that space between methodical progress and impatient curiosity, rumors thrive. But the real story is still unfolding. 3 Atlas has not finished its journey, and its true nature remains only partly revealed. As it swings past the sun, reemerges into view, and perhaps offers future opportunities near Jupiter, the world will finally see more of this enigmatic interstellar traveler. For now, all we can do is wait, watch, and wonder what secrets 3I Atlas still carries from the stars.